The Best of Our Knowledge explores topics on learning, education, and research. Coming up, imagine seeing something brighter than 10 trillion suns. Seems impossible. Well, scientists have detected a black hole flare that achieved this rare, unbelievable brightness. This sighting opens up the possibility of there being more flares of this magnitude. We will learn all about this supermassive black hole flare. You're listening to The Best of Our Knowledge. I'm Madeline Reynolds. Does the thought of something being 10 trillion times brighter than the sun seem impossible? Well, actually it's not. And don't worry, you won't see it. So your eyes are safe. Millions of miles away, a supermassive black hole unleashed a violent flare in 2018. It was at its peak intensity in 2023, shining with the power of 10 trillion suns. How did this happen? Astronomers believe the black hole devoured an unlucky star or a similar object. The destruction of the star caused the luminous blast. The black hole was recorded to be 30 times more massive than the sun, and that likely affects the intensity and power of this specific flare event. Now, many astronomers and scientists are classifying this as a record-breaking flare event, the brightest ever recorded. I spoke with Matthew Graham, a research professor of astronomy at the California Institute of Technology, to learn more.
Black hole is actually it's a sort of generic term because it covers essentially about a black hole is something which is so dense that light can't escape from it. So once you get too close to it, that's it. You're going to go straight into it, and we'll never hear from you again. Now, the term black hole actually covers a very large range of mass. So we can have black holes which are, the mass of the Earth. More commonly, we think about solar mass black holes, which are the end of a lot of the most massive stars' lifetimes. They'll collapse and they end in a stellar mass black hole. But we also have supermassive black holes, which sit at the center of most of our galaxies, and those are typically 1 million, 10 million, 100 million times the mass of the sun, rather than a stellar mass black hole, which is, typically maybe 1 to 10, 20 times the mass of a sun. So there's a wide range of what black hole encompasses. And we think that the supermassive black holes were probably formed very early on in the universe because, you need a lot of matter to be very close together to be able to create something that dense that it collapses. And then they grow through galaxy mergers as the universe progresses. Whereas the stellar mass black holes we see around are, as I said, the more likely to be the endpoints of stellar evolution.
Could you also explain to us what flares are, solar flares in space as well?
Yeah. So a galaxy which has a supermassive black hole in the middle, we call that an active galactic nucleus. If it has material around it that's falling into the supermassive black hole, it's what we call an accretion disk, a disk of material. It's like a whirlpool in a bath. Think of it that's the material swirling down and being sucked down, and that's the black hole in the middle. Now that material falling in gets really bright, and so we can see these things at a long distance, great distance away in the universe. And we've known about them for about 60 years, but we still don't really understand what's going on in the middle. It used to be that we thought we've just got this black hole there, and it's just got material that's falling in, and it's a burbling system. The material's just slowly getting sucked in, so it's like a very calm bath when you pull the plug out, and it just slowly drains away or something like that. But then we notice that they're also variable in the sense that their brightness changes with time in a way that we can't really predict. And sometimes their brightness really flares up. Something has happened close to the supermassive black hole or associated with it in that accretion disk um, that is not this regular burbling along. It's a sudden big outburst of energy. Um, and that's what we would call a flare in this context. Um, those are interesting because they're rare and we don't know what they are. But we hope that they'll tell us something about that environment.
So, how did you conduct your study into this black hole blast? What was the mechanics of understanding that and the results?
Yeah. So I've been involved in sky surveys for a long time, actually 30 years since I was a grad student. So the idea with the sky survey is you have a telescope and you look over a large region of sky and you keep doing that over and over again. And so you build up a picture of how the things that you're looking at are changing with time. And one of the things we're really interested in are the things which change very rapidly. And back in 2018, we were in a transition between two sky surveys, between the Catalina Real-Time Transient Survey, and which was ending, and then the Zwicky Transient Facility, which is the survey that I run, which was just getting started. And one of our regular, what has changed in the sky over the last 24 hours type thing, picked up this particular object getting brighter by quite a bit. And so we go, oh, okay, that looks interesting. Well, let's see what we can see about what it's been doing. Let's go back through the previous observations of that area of sky to see how long it's been getting brighter, how much has it gotten brighter by, and that sort of pushed it into the realm of being interesting enough that we will sort of go, oh, right, okay, well, it doesn't look like some of the things we would normally see doing this. It doesn't look like a supernova, for example, a star exploding at the end of its lifetime. So it's sort of okay, and it's associated with a galaxy um, or a very faint galaxy. Okay, so we'll try and get a spectrum of it to see what it might be, because the spectrum gives us the breakdown of the light from the object, and then that allows us to determine what sort of object it is and how far away it is and how energetic it is. So we got a spectrum. So we detected it getting bright sort of May, June in 2018, and then we got a spectrum in November, because it goes on a list somewhere, and you wait until the list is big enough and things like that. And the spectrum we got wasn't particularly great. It was a bad November night in 2018, and what we could tell was it was hot and blue. And so we thought, oh, right, okay, it's associated with a supermassive black hole. But because we couldn't really distinguish anything particular in the spectrum, it was what we call featureless. Um, that normally means we're probably looking at what's called a blazar. And a blazar is a type of supermassive black hole which has a jet of material coming out from it, and the jet is pointing straight at us. So they are very variable because what we see is a lot of variation in the jet. But it's not all the variability we see is associated with the jet rather than with the accretion disk and the supermassive black hole. So we thought of okay, yeah, there are other people who are more interested in blazars. At the time, I wasn't one of them, and so it's okay, it's a blazar. We'll forget about it. And then about 5 years later, we were doing a review of things that we had looked at in the early days of ZTF, and we went back to this particular one because we had taken a spectrum, and we noticed that it had been steadily declining over the past 5 years, which is not a sort of behavior you would normally associate with a blazar. And it's, oh, okay, this is something more unusual than we thought initially, so we need to get another spectrum. And this time it was the middle of the year, so the conditions were much better, and we got a spectrum which then showed broad emission lines, which tells us that it's a supermassive black hole with a disk around it, that it's an AGN, um, rather than a blazar. But it also allowed us to figure out how far away it was because we could measure the redshift from the spectrum. And that told us then suddenly, oh wow, this is actually quite far away. This is, 10, 11 billion light years away. Um, oh, and that means when we do the calculations, then it's actually more energetic than we thought it was, and that really pushes it into an extreme area of parameter space where we haven't seen stuff before. So it's suddenly big. It's that 2023 spectrum which really sort of went, oh, okay, yes, no, this is the sort of not smoking gun per se, but this is the crucial bit of evidence which links everything together and makes this something now where we need to invest a lot of more time to study it.
You're listening to the best of our knowledge. I'm Madeline Reynolds. If you're just joining us, we're learning all about the supermassive black hole flare with Matthew Graham, a research professor of astronomy at the California Institute of Technology, to learn more. So, in the research, it defines cosmological time. Could you just tell us what that is and its relation to this study?
Yes. Okay, so the universe expands, we know that. And that means that how we measure time changes in the sense that time sort of gets stretched as the universe expands. So it means that we call this time dilation, and it's in this particular case, it's caused by the expansion of the universe. So what that means is that very early on in the universe, a particular time period will seem much longer when we look back at it from the vantage point of the Earth, just because things have got stretched with the expansion of the universe. So in the case of this particular object, um, it's about a factor of 4. So 1 week there is a month here. So we're sort of looking at it at quarter playback speed, which is good for studying, but it also means things take a long time. So here we are in 2025. So it's 7 years later. But as far as the flare and the event is concerned, only 2 years has gone past. So it's going to take us 20 years here to see 5 years worth of activity over there. So this is a long, slow game in that regard. And that's just one of the things you have to deal with when we're going to be looking at more of these high redshift things as James Webb starts finding more things and the Roman Space Telescope's finding more things. So this is going to be a more common phenomenon now.
So, also in the research, it explains and defines what most likely caused this
Yep.
outburst, which is a tidal disruption event.
Yeah.
So, can you tell us what this means and the relation to the outburst that occurred?
Yes, sure. So for a long time, as I said, we used to think that supermassive black holes just sort of sat there with gas going around them, or maybe not with gas going around them. Maybe they were what we called quiescent, and they're just sort of sitting there doing absolutely nothing. Um, like your bathtub once all the water is gone. But we now know that there is a population of stars in orbit around supermassive black holes. We see this in the Milky Way with the supermassive black hole in the middle of our own galaxy. There's a population of stars going around it. And we call that a nuclear stellar cluster. And sometimes one of those stars in the nuclear stellar cluster gets too close to the supermassive black hole. And when it does that, it gets pulled apart. It gets shredded, spaghettified. Um, and that material then falls into the supermassive black hole and it releases a large amount of energy. Um, and that's what we call a tidal disruption event. Most of the tidal disruption events that we've seen or that we've studied are around these quiescent black holes, where they're just sitting there doing nothing and there's no previous activity of accretion disk. In this case, we have evidence that this particular object already had an accretion disk around it, but a more massive star, in the sense that most of the normal tidal disruption events we see are sort of stars about the sun's mass, maybe half the mass of the sun to sort of double, something like that. But in much rarer cases, we see more massive stars being pulled apart. And in this case, we think it's a star which is at least 30 times the mass of the sun, and maybe as much as 200 times the mass of the sun. Now, normally those types of stars are much rarer. In the normal galactic population of stars, they're maybe 1 in 1,000 are that massive. However, theoretical models of the environments of supermassive black holes with these nuclear star clusters and the gas and all that sort of thing make us think that maybe more massive stars, there are more massive stars in the environment of a supermassive black hole than normal. So maybe 1 to 2% of the stars around a supermassive black hole are these massive ones. So we should expect to see the tidal disruption event of a massive star around a supermassive black hole. And when that happens, it's going to be a very energetic event. And that's what we think we've seen here. So we think that there was this massive star living in the disk, and it hit something probably because that's the most likely way you get it to suddenly go in much closer to the supermassive black hole. And it got knocked onto a chaotic orbit, and that just brought it too close to the supermassive black hole, and it then just got shredded, releasing all that energy.
So, can we talk about the light and the brightness? Because that's really the
Yes,
thing that grabbed my attention about this. And it
yes.
said that it was 10 trillion times brighter than the sun. That almost seems impossible that there could be something that bright. I mean, how, first off, and how did we record that as well as, figure out how bright it
Right.
was and like how it travels? I mean, it's crazy.
Yeah, so the advantage is that it's very far away. So it's really bright where it's happening, but when we see it, it's much fainter because it's so far away. So I think we figured out that if it was at the distance of one of the stars in the Orion Nebula, Orion constellation rather, it would probably be as bright as the sun. But distance really helps us here. So the only way we can see these really bright things when they're so far away is with big telescopes, and that's how we did that here. But yeah, at its peak brightness, it's 10 trillion times the average brightness of the sun. Now, um, the amount of energy it's pumped out to date is probably the same as if we took the sun and converted it all to energy through E equals mc squared. So there's a lot of energy. It's very energetic. But again, it's so far away that we just detect it as, something getting brighter by a certain amount. And it looks like all the other things that get brighter by that. There are lots of things at that level. Um, and so it's a very faint thing for us here on Earth at that distance. We'd need to be much closer to it for it to be really, really bright. So distance is our friend here.
So you kind of talked about how the star kind of got too close and it was
Yeah,
absorbed, and therefore its energy, once the outburst happens, sort of like goes back out. My
yeah.
question is, so what happens to that material and the space around it? Does this outburst affect anything besides itself? Like, does it affect anything else in the galaxy that's around it, including the star material that's put back out?
Uh, Probably to some extent. So, what's happening is that the material is being shredded. So, the star's being pulled apart, and that material is then joining the other gas and whatever that's in the accretion disk and falling in onto the supermassive black hole. So that material will eventually go into the black hole, and we'll never know anything about it again. Um, but there is, as you say, there is this brightening from the event, which is irradiating the environment around the supermassive black hole and probably causing, um, heating of other gas and things like that. Um, we think it might be driving actually an outflow of material. We see some evidence for that in the spectrum. And there may be other things that we're looking to see. We're looking to see maybe we see a jet or something at some point in the future, because we see this with a lot of other tidal disruption events that after 4 or 5 years we see in radio wavelengths jets forming, and so maybe that's going to happen here as well. So there are ongoing things that we want to see whether it happens or not to understand this class of phenomena better. But it's just, I mean, it's a very hot, bright environment generically, and this is just suddenly there's a new hotspot there, which is heating its environment a bit more, but nothing more than that, probably.
You're listening to the best of our knowledge. I'm Madeline Reynolds. I've been speaking with Matthew Graham, a research professor of astronomy at the California Institute of Technology, to learn more about the supermassive black hole flare. So, is this cosmic black hole outburst like a record breaker in terms of brightness? Because I've never heard of something being 10 trillion times brighter than the sun. Is this like a super rare event in this
Uh,
case?
yes, so we know about 5 million AGN at the moment, active galactic nuclei, and so this is at least a 1 in a million occurrence. It's superlative in a number of ways, but I'm very cautious about saying it's the brightest because I will have colleagues who will go, no, 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 no. There was this event here, and there are other things that can be more energetic. This is certainly, I think, the brightest thing we've detected in the optical from an AGN, um, and probably the most energetic in that sort of regard um, through this class of phenomena. It is a very rare thing. And the other thing is that we have to look so far back. So we have to survey such a large volume of the known universe to find just one of these. That sort of tells us how rare these things probably are. But I expect that we will find others as we sort of know a little bit more now what to look for. So,
Yeah, and this kind of leads into my next question for you is like, do you believe this happens elsewhere, maybe to a lesser degree? Is things like that more common at a smaller level, these outbursts, or even this like, super event, there's a possibility there's one that we just haven't discovered yet?
I think both actually. I think there will be something brighter than this at some point, um, without a doubt, because that's how it always goes. But I think, as I said, a lot of the tidal disruption events we know about so far are around quiescent black holes, stuff that's not active. And that's partly because they're easier to detect because you don't have to worry about misidentifying the regular burbling activity of the gas falling in to look like one of those. I think there are probably a lot more of these things happening in the black holes which have the gas around them, and that's one of the things we're looking for now is to sort of get a handle on that. And it may be that some of those are very energetic, but because of the geometry of the system with all that gas, there may be obscuration and dust clouds making things actually fainter than they are, all sorts of things like that. Um, so that may be affecting some of our detection rates. But yeah, no, I think we're going to find more. And this sort of validates, as I said, this idea that there are these more massive stars around the supermassive black hole. So something has to happen to those. And so, maybe there's new simulations will give us a better idea of the sorts of things that those can do. And then those are sorts of things we can look for as well in the data.
What do you find the most fascinating about this research for you? What was most fascinating for you about it?
I like finding weird things in the universe, and just this was a good superlative one. The fact that it's so far away and so bright, and that it ties in this idea of these more massive stars. The fact that it sort of does validate some of our theoretical ideas of what might be out there, I think was great. But no, just it's a whole detective story, and just through happenstance, we did nothing for this for 5 years, and then we went back to it, and then we realized how significant it was. And that I really like that aspect of it, even though it was maybe bad science on my part to not do that. Oh, we should have stuck with it, and then we would have got more data on it or something like that. But I think it's just it also shows that even though we're doing all these big surveys and whatever, there's still a lot to discover out there. And particularly in supermassive black holes, which is what I do, I think it's still a really exciting field with a lot to find out.
And then my final question for you is, what would you like to research next? Maybe into this topic or something different? What's on your plate next?
Yeah, so that's an interesting one because the publication time for scientific results takes a while. So a lot of the work we did on this was all written up a year ago. So this is a little old for us in some ways. So there's new stuff we're looking at now, which is also exciting. I think the thing I really like are these supermassive black holes and the really weird ones, the most energetic ones, or the ones which are doing things. And there are stars, and what can they do? Do they, particularly with these tidal disruption events, does the star get eaten in one go, or does the supermassive black hole have several bites at it? And does it matter if it's going clockwise or anti-clockwise in regard to that? And does that change things like that? So I think there's a range of phenomena that we're going to be looking for now, or that we are looking for, and trying to find all the different ways in which these systems can configure themselves, and what that tells us about them. Um, and I think, and the other thing is that these are long-lived phenomena. As I said, it's taken 7 years here to get 2 years there. So we can certainly look at this for another 10 years and see what it does over the remaining 2 or 3 years. Because the systems are big, and that's why it's slow. When it's 100 million times the mass of the sun, the supermassive black hole, things don't happen very quickly. It takes days or weeks or months or years, and so I think that's another thing that I quite like. And so it's building up these long data sets and then going through them with AI to find the things that are interesting, stuff like that.
That was Matthew Graham, a research professor of astronomy at the California Institute of Technology. His research was originally published in the journal Nature Astronomy. This has been The Best of Our Knowledge, episode 1833. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Madeline Reynolds.